section 2.6. In your textbook, right? So let's pick it up where we left off. We were discussing limits at infinity. So let's discuss some facts about limits at infinity. Number one, something goes to 0 if and only if its reciprocal goes to plus or minus infinity. Okay. Doesn't have to go to both. It can be just one or the other. Okay. So an example, the limit of x squared as x approaches 0. Well, you know that limit is equal to 0, right? What about the reciprocal of x squared? The limit of 1 over x squared as x approaches 0. Doesn't exist. As x approaches 0, 1 over x squared increases without bound. Okay. That's what this is saying. If x squared goes to 0 as x goes to 0, then 1 over x squared increases without bound as x goes to 0. Okay. The limit is x squared. The limit of x squared is x increases without bound. Excuse me, I meant to do 1 over x squared. I'm sorry. I meant to do 1 over x squared. The limit of 1 over x squared as x increases without bound is equal to 0. What about the reciprocal of 1 over x squared? As x increases without bound, x squared increases without bound. So the limit of x squared as x increases without bound is infinity, because x squared increases without bound. Okay. The second fact, if p is a constant, the limit as x increases without bound of x to the p power say is infinity, or x to the p is increasing without bound, as x increases without bound, if the exponent p is positive, greater than 0. And that limit is equal to 0 if the exponent p is negative. So as an example, let's use p equals 1/2. When the limit as x increases without bound of x to the 1/2, so x to the 1/2 is positive, x to the 1/2 is the square root function, right? This graph looks like this, right? X-axis, y-axis, origin. And so as x increases without bound, square root of x increases without bound. Okay. Now let's do a negative value of p. P equals -3. So p is equal to -3, but p is negative. Well, x to the -3 power is the same as 1 over x cubed, right? So this is equal to and so as x increases without bound, 1 over x cubed goes to 0. So p of x is a polynomial, and LT sub p of x is its leading term, right? LT is short for leading term. Okay. P for polynomial. Independent variable is x. If p of x is a polynomial and LT p of x is its leading term, then the limit of the polynomial p of x as x increases without bound is equal to the limit of the leading term as a function of x as x increases without bound. Okay. And with this fancy notation, you may not realize this, but we did this in pre-calc. This is talking about the in-behavior polynomial functions. And we talked about the in-behavior polynomial functions in pre-calc. The right end either goes up or it goes down. The left end either goes up or it goes down. Remember that? So this is fancy notation for the end behavior of polynomial functions, right? Graph of polynomial functions. We're just talking about the end behavior, right, of polynomial functions, and the graph either goes up or goes down on each end. Right? We did that in pre-calculus, right? So on each end, the graph either goes up or it goes down. Okay? Yes, sir.
What's that thing in front of the T and the P?
Where?
The symbol in front of the T and the P.
It's an L.
That's an L.
It is an L.
Maybe would it be better if I did like that?
I guess I didn't know that.
Say what?
And just go one, which doesn't make sense.
So it's just LT is just for, it's supposed to be LT for leading term. Okay. Yeah. LT. Gotcha. For leading term. That's what it's supposed to be. Okay. So let's do an example. So let's say we have P of X is equal to the polynomial 5x cubed plus 2x squared plus x minus 7. So the limit of that polynomial as x increases without bound, okay, is determined by the leading term, right? The leading term is the term with the largest power of x. The largest power of x is x cubed. And so the leading term is 5x cubed. And so the limit of this polynomial as x increases without bound is driven by the leading term. Determined by the leading term. And in pre-calculus, when we were determining the end behavior of polynomial functions, we looked at the leading term, and then based upon the leading coefficient and the degree of the polynomial, we determined whether the right end goes up or down, or whether the left end goes up or down. But instead, now we're using a limit to determine the behavior of the right end. Right? This is right end behavior because x is increasing without bound. Okay, it's the far right end of the x-axis. Okay. Well, as x increases without bound, x cubed increases without bound, right? The graph of 5x cubed looks like this. If you remember graphs of the cubing function from pre-calculus. And so the larger the value of x, the larger the value of y, right? The larger the value of the function 5x cubed. And so five x cubed increases without bound as x increases without bound. Which means the right end in the graph goes up. Okay. left-in behavior. We do as x decreases without bound, right? And if you want for just a second, you can, minus infinity is not a number, right? It just means decreasing without n, without bound. But if we put minus infinity in for x here, we have 5 times minus infinity cubed, right? When x is decreasing without bound, x is negative. And negative cubed is negative. And negative times positive is negative. Right? So this is positive, that's negative, and positive times negative is negative. So as x decreases without bound, 5 times x cubed decreases without bound. And so the left end goes down. Now, I graphed 5x cubed because I'm familiar with the cubing function. But if you're not familiar with the cubing function, you can determine whether the right end goes up or down and whether the left end goes up or down with the limit. Okay. All right. So any questions on that? One more fact. And we'll use these facts and work in some examples. So this is fact number 4. All right. This you have also seen, right, in pre-calculus, but not in terms of a limit. If p of x and q of x are polynomials, then p of x over q of x is called a rational function. Okay? We studied rational functions in pre-calculus. And rational functions may or may not have horizontal asymptotes. Okay? And so what this is saying, to determine the right end behavior, right, x is increasing without bound, to determine the right end behavior of this rational function. Okay? All we have to do is look at the limit as x increases without bound of the ratio of the leading terms. And if you remember, that's what we did in pre-calculus, right? Remember we talked about top heavy, bottom heavy, equal degree. Okay? And so if the degree of the polynomial on the numerator and denominator were the same, there was a horizontal asymptote, and you just took the ratio of the leading term, or of the leading coefficients, to find the equation for the horizontal asymptote. So, taking the limit as x increases without bound, right? That's determining the right end behavior. of the polynomial, right, of the rational function. So, in pre-calculus, okay, in determining the end behavior of rational functions, right, we use terms like bottom heavy, top heavy, and equal degree. Maybe that's sparks some memories, okay? And so, if the two polynomials are equal degree, then the equation for the horizontal asymptote was the leading coefficient of p of x in the numerator, okay, divided by the leading coefficient of q of x in the denominator. Okay, just to give you try to remember a little bit. If it was top heavy, remember there was no horizontal asymptote. Now I'm going to use the initials. No horizontal asymptote if it was top heavy. Do you remember what the equation of horizontal asymptote was if it was bottom heavy?
Someone said it be, oh, no, that's a 15.
Do you remember? Y equals 0, right? It's the x-axis. Y equals 0. Trivia is good. Right? Helps us to reinforce our learning. Okay. All right. So we'll do some examples to illustrate these facts. So we're going to evaluate some limits.
Professor,
Yes, ma'am.
wasn't there another case as well that we need to be concerned about if it's the top is 1 degree larger than the bottom?
Oh, that's right. There was this slanted asymptote. Yeah. And with slanted asymptote, right, you might have a situation where a function goes like this, right? And so there was a slanted asymptote, but technically, it's still going up forever on the right end.
Okay.
Yeah. Okay. That's a good reminder. I forgot about that. Okay, thank you. All right. Yeah, so this is the case of a slanted asymptote, if you remember. All right, so let's evaluate some limits, okay? So we have limit as x increases without bound of x to the 1/3 minus x to the minus 4th power. Okay. And so we're going to be using fact number 2. Okay. Well, x to the minus 1/4 is the same as 1 over x to the 4th, right? So as x increases without bound, 1 over x to the 4th is going to what number? I think I actually used this as an example, right? It's going to 0, right? Prove that with the table of values, right? We graph this function, okay. Similar ones to it, right? So the graph of 1 over x to the 4th for positive values of x looks like this. So the larger the value of x is, the closer the function is to 0. Value of the function is to 0. What about x to the 1/3? As x increases without bound, what does x to the 1/3 do?
Slowly gets larger.
Is it increasing without bound? At a slower rate, right? But it's still increasing, right? Because the graph of x to the 1/3 for positive values of x looks like the square root function, right? Like x to the 1/2. So the larger value of x is, right, the larger the value of x to the 1/3 is. Okay? And you can verify all this with a table of values. Okay? And so this is getting back to fact number 2, right, that we did already, that we wrote on the board already. So just to put this in limit notation, as x increases without bound, x to the 1/3 is increasing without bound. Okay? And as x increases without bound, we have 1 over x to the 4th going to 0. So this guy is right, x to the 1/3 is increasing without bound, and 1 over x to the 4th is going to 0. So this difference, kind of be thought of as infinity minus 0, is increasing without bound.
So wait, I thought at first we said, oh, it's approaching 0.
1 over x to the 4th is approaching 0.
Okay.
Not the whole thing,
That makes more sense.
right?
Yeah.
That's what I wrote down here. Right. X to the 1/3 is increasing without bound, and 1 over x to the 4th is going to 0. Okay.
So why is it ultimately increasing without bound? Yes.
Because as x increases without bound, this increases without bound. And this goes to a fixed number, 0. So this just keeps getting bigger and bigger and bigger and bigger and bigger and bigger. Why this gets close to 0. So you got something really big minus 0. Okay. So, I mean, just to illustrate, we have a function f of x is equal to x to the 1/3 minus 1 over x to the 4th. Okay. F of 1 is equal to 0. And remember, 1/3 means cube root. So f of,
This is number 5. This is the next fact, yes.
no,
No, same one.
we're evaluating limits. We're doing examples.
Okay.
There's only 4 facts.
Okay.
Okay. So f of 1 billion, okay, is equal to the cube root of 1 billion minus 1 over 1 billion to the 4th power. Okay? Well, the cube root of 1 billion is 1,000. And minus 1 over this number is basically 0. So you can see, in going from 1 to 1 billion, right? This function is increasing. It's not converging to any number. It's increasing without bound. Okay. So to convince yourself of these things, you can always use Excel and create yourself a table of values like we've done in class, where I start x equals 1, x equals 100, x equals 10,000, x equals 1,000,000, and so forth, right? As x increases without bound, what's the function values do? Okay. You can always use Excel or something like that. Okay. All right. The limit as x increases without bound, 4x to the 5th minus 2x to the 4th plus 3x plus 1. Well, that's a polynomial in parentheses, right? And so, in determining the behavior of this polynomial as x increases without bound, right? We don't care about the minus 2x to the 4th plus 3x plus 1, because 4x to the 5th is the leading term. And so we're using fact number 3 from the previous page. And this limit is just determined by the leading term. This is equal to the limit as x increases without end of 4x to the 5th. As x increases without bound, what does 4x to the 5th do? Yeah, right? So x to the 5th, as x increases without bound, x to the 5th increases without bound, right? It's kind of like infinity to the 5th power, which is infinity times 4. So plus times plus is plus, so this increases without bound. So on the graph of this polynomial, the right end goes up. Okay. In pre-calculus, you determine that the right end goes up just by looking at the leading term. But here we're using limits to show that it goes up.
So if 4 was negative on that, then it would go down, right?
Yeah.
Okay.
Yeah.
So we
Because
can-
it would be like minus infinity to the 5th, and a negative to an odd power is negative. You get negative times positive, which is negative.
Okay.
Yeah. So I want to emphasize, we don't, infinity is not a number. But we're sort of treating it like one for just a second to see whether this is positive or negative. If it's positive, then the limit, right, of this function is increasing without bound. If this function is increasing without bound as x increases without bound. If it's negative, then this function is decreasing without bound as x increases without bound. All right. So here's a rational function. And x increases without bound is right end behavior.
So do we only tell the right side?
Now it just turns out this way. But we'll be looking at some going to minus infinity. Okay. I just want, you know.
Yeah.
All right, you guys. Pre-calculus. Rational function. Does this rational function have a horizontal asymptote?
Yeah.
So if it has a horizontal asymptote, what's the equation? Yeah, y=2, right? Degree 1 over degree 1 equal degree. So you take the ratio of the leading coefficients, which are 2 and 1. 2 over 1 is 2. So y=2 is the equation for the horizontal asymptote. But you know what? You don't get to cheat. Okay? On the exam question, right? Basically, you gotta be able to show, okay, that indeed is the case. Okay. So we got to do some algebra. We're going to prove that this limit indeed equals 2, and so y=2 is a horizontal asymptote. So we're going to divide top and bottom of this quotient by the largest power of x in the denominator. The largest power of x in the denominator is x. So we have 2x minus 1 divided by x in the numerator, and x plus 3 divided by x in the denominator. Now I'm going to do some extra steps in this first one, but eventually we're going to skip these extra steps. Okay? So 2x minus 1 divided by x, right, is the quotient 2x minus 1 over x. And x plus 3 divided by x is the quotient x plus 3 over x, right? Remember, fraction bars are like division symbols. And now we're going to rewrite the quotient in the numerator and rewrite the quotient in the denominator. Okay. So when you divide 2x minus 1 by x, you got to divide 2x by x and the minus 1 by x, right? Division does not undo the subtraction. So we have 2x over x minus 1 over x. Again, you know, this step here and this step here, right? I'm not going to do it every time. Okay? I just want to remind you about division. And then x plus 3 over x is x over x plus 3 over x. Well, 2 over x, so 2x over x is just 2. And x over x is 1. Now, one thing we're not doing, you know, we studied the limit laws, right? We understand what they are. We're implicitly using them. I'm not going to rewrite this with the limit in the numerator, limit in the denominator, and then take the limit of each term. We understand those laws. Okay. Well, as x increases without bound, 1 over x goes to what number? 0. And 3 over x goes to what number? 0 as well, right? Because 3 over x is the same as 3 times 1 over x. And 1 over x goes to 0. 3 times 0 is 0. Okay. So the constant 3 in the numerator doesn't keep 3 over x from going to 0 as x increases without bound. So this is equal to 2 minus 0 over 1 plus 0. which is equal to 2.
Could you just repeat where the zeros came from?
Okay, so let's use right into limit laws. This is equal to from the limit laws, we're taking the limit of a fraction. So this is equal to the limit as x increases without bound, 2 minus 1 over x, over the limit as x increases without bound, 1 plus 3 over x. By the limit laws. And now I can take this limit inside the parentheses, and this limit inside the parentheses. So we have the limit as x increases without bound, 2 minus the limit as x increases without bound, 1 over x. In the denominator, this is the limit as x increases without bound of 1 plus the limit as x increases without bound, 3 over x. As x increases without bound, 1 over x goes to, and 3 over x goes to, so this is equal to, and the limit of a constant is just a constant. So we have 2 minus 0, 1 plus 0, which is 2. Okay. So that's what I mean. In this, we're implicitly using the limit laws, right? Not explicitly. Okay.
Can you define that actually?
What?
I don't understand what you mean by word.
Well, we know that we're applying the limit laws when we jump from here down to here. Okay? Right. We know we're applying them. We're just not explicitly writing them out on the board. All right. Okay. Any questions on that? All right. So, you guys told me the horizontal asymptote was y equals 2, right? And so that's what the limit is. Maybe if I slow down, I can actually draw an infinity symbol. All right, this is a rational function, ladies and gentlemen. Does the graph of this rational function have a horizontal asymptote?
Yes.
What's the equation? Y equals 0. So we're going to prove that this limit is equal to 0. So we're going to divide largest power of x in the denominator is x squared. So we're going to divide top and bottom by x squared. So we have 3x minus 1 over x squared over 3 minus x squared over x squared. And so in the numerator, we have 3x over x squared minus 1 over x squared. In the denominator, we have 3 over x squared minus x squared over x squared. Well, 3x over x squared simplifies to 3 over x. Remember, this is the main fraction bar right here. So, as in the main numerator, as x increases without bound, 3 over x goes to what number? 0. As x increases without bound, 1 over x squared goes to what number? How many of you guys look at fact number 2? Okay. So by fact number 2, 1 over x squared goes to what number as x increases without bound? 0. Okay. Fact 2. Three over x squared goes to what number? Well, the numerator is 0 minus 0 is 0. The denominator is 0 minus 1 is negative 1. And 0 divided by any non-zero number is. And so we just proved that the horizontal asymptote is indeed y equals the horizontal line y equals 0. You'll learn these. Don't worry. You'll learn. Okay. You'll get so good at this, you'll breeze right through it in no time. Okay. If you're never sure, right, you can always do the table of values that we've done. Where you pick some values of x, then you calculate the corresponding values of the function. See what the trend is. All right. So let me ask you, I gotta be careful how I'm gonna ask a question. This is a rational function. Does it have a horizontal asymptote?
Maybe a slant no.
No, it does not have a horizontal. Yes, it has a slanted. Okay. Well, if it doesn't have a horizontal, but it has a slanted, then this limit, right, as x increases without bound, the limit of this function as x increases without bound, this one, it's not coming out right. This function has to do what? if there's no horizontal, the limit of this function has to be what if there's no horizontal asymptote but a slanted asymptote. It either keeps going up or it keeps going down, right? That has a slanted asymptote, okay? But slanted asymptotes either go up forever or they go down forever. Okay. All right, so let's determine, does it go up or does it go down? Okay. So the largest power of x, the denominator is 1. So we're going to divide top and bottom by x, by just x. So we have 2x squared plus 3x plus 1 over x over 3 minus x over x. Well, so remember, so we got to divide 2x squared by x, 3x by x, and 1 by x, right? So 2x squared divided by x is just 2x. 3x divided by x is 3. Then we have 1 over x. In the denominator, you got to divide 3 by x, and then you got to divide x by x, which is 1. Okay. So now this is where I'm skipping steps. I'm not doing each tiny step. Okay, so you should understand this now. Yes, ma'am.
You said divide by the largest power of x in the denominator?
Yep.
Okay.
Which is x. Okay. And we did the same thing over here. Largest power of x in the denominator, right? It's 2. So we divided top and bottom by x squared. Okay. Well, as x increases without bound, 1 over x goes to what number? 0. And 3 over x goes to what number? 0. Well, we got to ask yourself, what about 2x in the numerator here? As x increases without bound, what does 2x do? It increases without bound, right? So let's note, as x increases without bound, 2x conversely increases without bound. Okay. And 1 over x as x increases without bound, 1 over x by fact number 2 goes to 0. And the limit of a constant is just self, right? So the numerator, oh, well, let's do one more. And then the denominator, 3 over x goes to 0. 3 over x goes to 0 as x increases without limit. Okay. Remember, rule number 1, fact number 1 says, if one thing goes to infinity, its reciprocal's got to go to 0. Right? That's what fact number 1 was. Okay. And we showed that using x squared and 1 over x squared. So, as x increases without bound, 2x increases without bound, 1 over x goes to 0. So this numerator here, 2x plus 3 plus 1 over x, 1 over x is going to 0, 3 is just 3, but 2 over 2x is increasing without bound. And so infinity plus 3 plus 0 is the infinity. Right? And so the numerator is increasing with a bound, we can just pretend for a second, okay? Like that's a number. Okay? And the denominator, 3 over x minus 1, is going to 0 minus 1, which is negative 1, right? And then say going to. As x increases without bound, 3 over x is going to 0. So 3 over x minus 1 is going to 0 minus 1, which is negative 1. So we have something positive over something negative. And a positive over negative is negative. So as x increases without bound, this rational function is decreasing without bound. So our slanted asymptote is going down, not up. And there's no obviously no horizontal asymptote. So the numerator is increasing without bound as x increases without bound. Because this goes to 0, but this just keeps getting larger and larger and larger and larger and larger and larger and larger, okay, without end. Okay. Any questions on that? All right, somebody was at, are we ever going to do one with x going to minus infinity? Yeah, we're going to do that now. Same problem, x going to minus infinity. So we should get, well, we don't, so this is right in behavior that we did, right? In a sense. Now we got to do left in behavior. Yes, sir.
For all the examples you've done so far, is it possible to do a left-hand behavior?
That's what we're going to do now.
Okay.
Yeah. So now we're going to do the limit as x approaches minus infinity, or as x decreases without bound. So this is left in behavior. And so we have the same rational function. 2x squared plus 3x. Oops, we do not have the same rational function. It's 2x squared plus 3x minus 1 over 3 minus x. You know what? I'm going to make it the same function. Change that. All right, doesn't matter. Okay. The constant doesn't matter. So I'm going to make it the same problem. Okay, same function. So, you know the first step is to divide top and bottom by the largest power of x in the denominator, right? Which is x. So we did that over here. Okay. Divide top and bottom by x. And then when we simplified, this is what we got right here. Okay. So we can skip those steps. And we have 2x plus 3 plus 1 over x over 3 over x minus 1, right? So I went from here to here. Okay. Don't have to reinvent the wheel. Okay. Now, as x goes to minus, as x decreases without bound, 2x, what's 2x going to do? Yeah, it's going to decrease without bound too, right? Because 2 is positive, so if x is negative, positive times negative is negative, right? So if x decreases without bound, 2x is also going to decrease without bound. What about 1 over x? Yep, it's still going to go to 0. Okay? As you divide, if x is minus a billion, 1 over minus a billion is still close to 0, right? And the same way with 3 over x. 3 divided by minus a billion is still close to 0. So we'll do like we did over here. So 2x plus 3 plus 1 over x. 1 over x is going to 0. And 0 plus 3 is 3. But 2x is going to, it's decreasing without bound, right? So minus infinity plus 3 is minus infinity, right? So the numerator here is decreasing without bound. And the denominator is going to 0 minus 1, which is negative 1. Negative over negative is positive. So on the left end, the graph is going up. On the right end, the graph is going down. Graph is going down on the right end, and it's going up on the left end. All right. So tomorrow we'll work a few more examples, okay? And then you'll have everything you need to do this homework. Okay. So I'll see you tomorrow.